Okay, thank you very much, Sonia, for this nice introduction. It is one of the greatest honors, really, for me to be invited to give this public lecture, and even more so in the presence of such esteemed audience. I apologize in advance for many omissions of names and works of people, also for the level of rigor, but this talk has to be kept at a basic level. So, as I assume that many people in the audience are not mathematicians, let me start slowly by reminding from the Wikipedia what is mathematics. So it is a field of study that discovers and organizes methods, theories, and theorems that are developed and proved, and I stress this, proved, for the needs of empirical sciences and mathematics itself. So, in the words of not a mathematician, but the famous physicist Richard Feynman, mathematics is not just a language, it is a language plus reasoning. And those who want to understand nature without the use of mathematics must settle for a reduced understanding. So, one cannot understand the universality of laws of nature, the relationship of things, without an understanding of mathematics. There is no other way to do it. So, the aim of this talk is to give some mathematical background of techniques that are used in, from knot theory, that are used in life sciences. In particular, now focusing more to topology, topology from the Greek word topos and logos is the branch of mathematics concerned with the properties of geometric objects that are preserved under continuous deformations. These are meant to be like stretchings, twistings, crumpling, and bending, without closing holes or opening holes or tearing or gluing or passing through itself. And with disregard the geometric properties. So we don't care about the rigid structure of the object, like distances, angles, curvature, and so on, only about some more basic properties that are preserved via topology. So, topological properties up to homeomorphism is the dimension of a topological space, compactness, connectedness, the number of holes. So for continuous deformations, we mean either homeomorphisms, what we call homeomorphisms, which are bicontinuous bijection, that is functions 1 and 1 and on 2. And homotopies, which are roughly speaking, squishing objects into other objects. So, for example, just to not let you with so many unknown words and stress you, a homeomorphism, the famous example is that the homeomorphism can turn a coffee mug into a donut. And so here we see a nice, nice models, a sequence that turns the coffee mug into a donut. These are ceramic made by Crane and Segerman. So a homotopy can squeeze the donut eventually. So first the coffee mug is turned into a donut. This is our favorite example of the topologists. And then a homotopy can further squeeze the donut into a circle. Then a circle is homeomorphic to a square because we don't care about geometry. Still, these objects do have some common features, like they are one-dimensional, they separate the plane into two regions, disjoint regions, and so on. Now, homeomorphism, talking of homeomorphism, a circle is homeomorphic to any knot. So, up to homeomorphism, we cannot really distinguish knots, which is our subject here. Nevertheless, topology is very flexible, but still captures essential features, as we see here. And here is another artistic image using topology, let's say. Now, let's go to some history topology. So this branch of mathematics started long way back. Leibniz envisioned the geometria situs and analysis situs. There was no topology at the time. This word was not invented at the time. Then, 18th century, Leonhard Euler, he found the problem of 7 bridges of Königsberg, this famous problem of trying to find a way to pass from all bridges only once. And also he invented the polyhedron formula, the number of vertices minus number of edges plus number of faces equals 2 for the cube, for example. And he's also known for the classification of surfaces, like that they are classified by the genus, which is the number of holes in the surfaces, meaning always orientable, connected. Okay, now let's move a bit on. Then we have Gauss, who used the term geometria situs. He really used it, he did not just envision. And then we have Henri Poincaré, who is the creator of algebraic topology. He's known for the famous Poincaré conjecture, and he used the terminology analysis situs for topology. So, trying now to go closer to the subject of knots, let's see. So, Gauss, in his works on electrodynamic theory, he showed some interest in knots, and in his handwritten notes, he made a catalogue of 13 knots, which he copied from the British Navy Academy handbook, and in fact, he really used the English names for the knots. So his student listing started working on the subject of knots, let's say studying knots also, but then it is not till William Thomson comes forward, later Lord Kelvin, who made the theory of vortex atoms, meaning that an atom was a vortex in the ether. So he tried through this theory to classify atoms. Of course, not soon, it remained as a theory for some decades, but then it is soon easily, let's say, convincing that knots cannot classify atoms because knots are infinitely many to start with, at least. But his theory influenced his collaborator, Peter Guthrie Tait, a mathematical genius in Cambridge, fellow of the Royal Society, who started tabulating knots and took about 20 years with this project. And imagine how he did. So he created curves on the plane, and at every double point, he made choice whether the curve passes over or under, the arc passes over or under, and then he made all possible, or roughly, let's say, all possible such curves, and then he reduced the results to see if it is knots that he has already classified, and or not. If not, then he considered adding them on his table. So that was, so you see in the early years, his table, 1877, and then somewhere in between, let's say. And then 1885, he gave a full list of knots up to 10 crossings. So this was an important legacy that he left to knot theorists and low-dimensional topology. And for many decades, mathematicians used his table, as copied in the book of Rollsen. And he also, during the study, he also formulated very, very important conjectures in knot theory. Little produced same catalog almost simultaneously. So, now, the work of Tite starts really the subject, formally, the subject of knot theory as a mathematical topic. So, let's go back to what are the classifications problem in topology and focusing to knots with the eye on knots. So, one is to classify spaces up to homeomorphism, like the surfaces that are two-dimensional spaces, or for three-dimensional manifolds, we have the Poincaré conjecture and so on. And the other is to classify embedded subspaces up to homeomorphisms of the ambient space. And this classification is up to isotopy. So, we said that every knot is homeomorphic to the circle. So, how do we tell apart? Through isotopy. This is what is good for us. So here we see the first three knots, the unknot or trivial knot, the trefoil, the figure 8. And here is like tables that we see nowadays with coding that Tite gave. And here at the bottom, we also see links of two components. So, knot theory, then, is the branch of topology that studies knots, and it interacts with practically all other areas of mathematics and has very important applications in physics, chemistry, biology, and other areas. A knot mathematically is a smooth closed curve in 3 space with no self-intersections, or else an embedding of the circle in 3 space. And a link on n components, like n rings, it is the embedding of n circles in 3 space. Okay, and as we said, the only appropriate notion for considering knots is up to isotopy. And we say that 2 knots are equivalent or isotopic if there is we can imagine an elastic deformation of the ambient space carrying one knot to the other. So here I ask if this knot is trivial, and here from this picture we start seeing the complexity of knot theory. So at this point, I want to bring up a knot plot and show you one video. So you see, this knot looks pretty knotted, and if we press here, you see that there is a continuous elastic deformation in space that brings it to trivial. So it is not knotted, really. So let's go now back to the slideshow. And continue. So we started the subject of knot theory. And the central problem of knot theory is the complete classification to give a full list of the infinitely many discrete objects called knots and links. Although very tough problem of extremely high complexity, we can still ask to start with some basic questions like, is this knot, the trefoil, isotopic or not to the circle? Or the circle, is it isotopic or not to 2 circles? I mean, our intuition says no, but mathematics need proofs. And this is the important that makes this area of study different from other scientific areas. Or can we prove that what we call Hopf link is not a trivial link on 2 components? Or the right-handed trefoil, is it isotopic or not to the left-handed trefoil? And how about the figure 8? Is it equivalent, isotopic to its mirror image or not? So the first big step towards the study of knots was done by Reidemeister, who, first of all, he thought of, okay, first of all, we discretize isotopy by considering polygonal curves in space, and then all these continuous elastic deformations can be discretized by what we call small delta moves in 3 space. Then Reidemeister thought of projecting the knots onto the plane paper, the blackboard, and instead of looking at 3D objects, better look at their projections with extra information of which arcs goes over and which goes under, because this is important. So, Reidemeister proved that 2 knots or links are isotopic if and only if any 2 diagrams of theirs projected anywhere differ by finitely many of these moves, which we call planar isotopy and Reidemeister moves. So instead of analyzing knots in 3 space, we can consider the projections on the blackboard, and isotopy moves then become discrete. As an example, we show here a diagram, a knot diagram, top, and then with a finite sequence of Reidemeister moves, we bring it to the knot. So this means that there is an elastic deformation in 3 space that brings this knot to the trivial. Okay, but then to make the theory more mathematical, let's move on. The classification problem in knot theory, and generally in other areas of mathematics, classification problems are tackled by constructing invariants, appropriate functions that respect the equivalence we set every time. So here our equivalence is the isotopy. So an invariant is a function from the space of all knots and links to some set. So it takes values like numbers or polynomials or other values like on, off, yes, no, and so on. So such a function is called an invariant if it respects isotopy, meaning that if 2 knots are isotopic, then the invariant I will give them the same values. So equivalently, this means that if an invariant gives to 2 knots, a specific invariant, gives to 2 knots different values, this means that they are not isotopic. Therefore, they are distinguished. So they belong to different places in the knot classification. And this is how the classification problem is addressed. So if a pair is not distinguished by some invariant, we try constructing or we try some other invariant on this pair. If it's still not distinguished, yet we go to another one. And then at some point, we may suspect that these 2 knots, after all, if they are not distinguished by all invariants we have in hand, maybe they are the same, maybe they are isotopic. In this case, if we start suspecting that they are isotopic, we may start trying to find a sequence of Reidemeister moves, bringing one to the other. Okay. But only if we really suspect, because otherwise we have no upper limit for Reidemeister moves needed. Only if we know, then we can find. That's what the Reidemeister theorem says. If we know that they are isotopic, then we can find a finite sequence of these moves. But if we don't know, then we go blindly. We have to try invariants. Okay, so some simple invariants are, for example, the number of components. So knots and links are told apart, and links with different number of components are also distinguished. Then, but of course, the number of components does not distinguish any of the knots between themselves. Another invariant is the crossing number, which is the minimal number for all possible diagrams we can have of specific knot. Take from all diagrams the minimal number of crossings needed to represent the knot as a diagram. So here we see the list. Knot with 3 crossings is the trefoil. And perhaps also it's mirror image. Then with 4 crossings, we have 1, the figure 8. With 5 crossings, we have 2. With 6 crossings, 3. With 7 crossings, we have 7, and so on. Another interesting invariant is the 3-colorability. What does that mean? We are given a diagram, and we say that this is 3-colorable if every arc of the diagram means from undercrossing to the next undercrossing. That's what we call an arc. If it can be drawn using one of the 3 colors in such a way that all 3 colors are eventually used, or at least 2 of the colors are used, and at any crossing at which the colors meet, all 3 colors must meet. Otherwise, it is not 3-colorable. So we see here, at least for these diagrams, we see that the trefoil is 3-colorable. Then, the method of distinguished knots using colorability of their diagrams was invented by Ralph Fox. So, the 3-colorability, first of all, I leave it as an exercise for you to show, using the Reidemeister theorem, that 3-colorability is indeed an isotope invariant. Then we see that from the rules, the trivial knot, the unknot, is not 3-colorable. The trefoil is 3-colorable. So knot and trefoil are distinguished. Then the figure 8 is not 3-colorable, so it is distinguished by the trefoil, but then 3-colorability does not distinguish the figure 8 from the unknot. So we must find some other invariant to distinguish these knots. And another famous invariant is the Gauss linking number. So we have 2 components of a link, and the linking number is defined as, so if we talk about closed curves, okay, the linking number is defined as the number of +1s signs plus number of -1s for every positive or negative crossing. So the link has to be oriented, the 2 components have to be oriented, and their crossings are positive or negative according to this rule. So this is the Gauss linking number. It's only for links, 2 components, any 2 components of any link. And here are some examples where we show that the linking number will distinguish now the Hopf link from the trivial link. Also, it will distinguish the Hopf link from this one, more complicated, again with 2 components. But, okay, it is a weak invariant, but it answers some basic questions. So here at the bottom row, we see the Whitehead link, which has linking number 0, although we see that it's quite linked, the two components are quite linked, and is the same 0 as the unlink. And here is another famous link of 3 components, the Borromean rings, which also are not distinguished by the 3-component unlink. And the Borromean rings have the nice property that if we remove any of the 3 rings, the other 2 fall apart. So it is the interlinkage, really, that pulls this link together. Then other invariants that have been constructed is the Alexander polynomial. This is to every knot, it assigns a polynomial invariant to every knot or link. Quite weak invariant, not so strong. And then we have the Jones polynomial, which was discovered in 1984 through the theory of von Neumann algebras. And this construction made Jones famous, and he was awarded the Fields Medal. And immediately, Lou Kaufmann, who is a famous mathematician and is in the audience, he is, in my eyes, the guru of knot theory, So I apologize to Luke Kaufman in advance if there are some inaccuracies here in my talk. So Luke Kaufman described almost immediately the Jones polynomial with diagrammatic methods. So he gave a huge service to the knot theory community. The bracket polynomial, which is given by the simple rules, every crossing is smoothed according to this, what we call skein relation. And inductively, we smoothen all crossings in the diagram, and we are left with a number of circles, which are called states of the diagram. And the basic rule of the induction is that the bracket polynomial of the unknot takes the value minus a squared minus a to the minus t, and the b variable is calculated to be a inverse. So this discovery gave really a new push to knot theory. And then the Jones polynomial is related to the bracket polynomial through this formula. There is just one multiplier here that is related to the right, but we'll see the right later again. For the Jones polynomial, no matter strong is not a complete invariant and is still an open problem if we can find a non-trivial knot with Jones polynomial 1 like the unknot. So this still resists solution. So after all this, we have a big set of invariants like the quantum invariants, the manifold invariants, Vasily invariants, Kovanov invariants, knot homology, and so on and so on. So these are the tools, the mathematical tools, as I said, for distinguishing knots and links, for telling them apart. So here I show some table that according to the crossing number, which is the minimal number for drawing a knot, and the minimal number of crossings, with the number of knots with this crossing number. And we see that up to 10 crossings, which is what tight completed, and little, like about 250 knots in 20 years, and without any invariants at hands. And then we see really how these numbers grow exponentially. So tight was almost infallible, meaning that really he distinguished with no invariants in hands, he distinguished all knots except for the Perko pair, which, let me show you. The Perko pair is, they look quite different, these two knots. They are both with 10 crossings, but Tight thought they are different, but Perko, a New York lawyer, found that they are the same. So these two knots are indeed isotopic. So I go back to the presentation. Okay, so, and yes, so the classification problem for knots is quite, it's a problem of very, very high complexity. Yet there are some families of knots that are fully classified. And one of these is the family of rational knots. So what are rational knots? So rational knots can be viewed to be obtained from three braids or, forget the word, from rational tangles. This is our viewpoint here. How? By starting, and again, and this is the last time I go to knot plot. Okay, so Rational tangles, how are they created? You start with two simple, unlinked, unknotted arcs, and you start twisting. A number of twists. And then you take two neighboring points, and you make some more twists, also from the top. And then you can make some twists from, again, neighboring points from one side, and then again from the other side. This is how we create rational tangles. And if we want to see the knot that is created, we take the numerator closure, or we could take the denominator closure. And this is how, I'm very glad I finished going back to, okay, to knot plot. I hope you enjoyed all these shows. Okay, so this is the family of rational knots. So we create a rational tangle. Okay, a rational tangle is represented by a rational number. That's where the name comes from, P over Q, where P and Q are prime to each other, relatively prime. So let's go a bit more in the fundamentals of this theory. Here we have the elementary rational tangles. We start twisting, and we have the horizontal rational tangles. And then if we start twisting two vertical arcs, we create the vertical rational tangles. And these are the elementary, let's say, building blocks for rational tangles. And this is a rational tangle in twist form, where we twist. So a rational tangle, in other words, is, as we say, a 2-2 tangle. 2-2 means we have two free ends up and two free ends at the bottom. So it is a 2-2 tangle, which has the property that we can find two consecutive ends from which we can start untwisting the rational tangle till the end. So here the two consecutive ends are this and this, as you can see. Okay, here are some examples of non-rational tangles. We cannot find two consecutive ends from which we can start untwisting. Here are rational knots. In this one, we cut here and create a rational tangle from where to untwist till the end. This is clear that we can cut the Hopf link and untwist. And these are non-rational knots. Okay. Now, for the rational tangles, generally for two tangles, we can define operations addition, like placing one next to the other horizontally and joining the two intermediate arcs. Multiplication, placing one on top of the other and joining these intermediate arcs. And there is the inversion. Using the addition and multiplication, we can present every rational tangle as the addition and multiplication outcome from the basic elementary tangles that I showed before. Now, the other thing is now that using this multiplication and addition, we can show that, the inversion, we can show that the multiplication by vertical tangle is reduced to this formula, which leads to a continued fraction formulation for rational tangles. In other words, for every rational tangle, we can assign, this is a proof, we don't need to follow the proof, but to every rational tangle, we can assign from the basic building blocks, which are the horizontal, these are integers, the horizontal or vertical twists that is composed of, the sequence of these integers gives rise to the continued fraction form of a rational tangle, and then now we see immediately how to correspond a rational tangle to a rational number. We just corresponded to the continued fraction that is related, that comes from these integers. So And Conway's theorem says that two rational tangles are isotopic if and only if, I mean, they are totally classified by the rational numbers plus infinity, the two vertical arcs. Then to move to classification of rational knots, we want now to try to understand if two rational knots are made as numerator closures A of two rational tangles. So they are, let's say, made out of two fractions. They are assigned two fractions. How are these fractions related? And here is one example. We take the tangle -3, so this one, and we take the tangle that comes as 1 crossing plus 1/2 vertical. We close those two, and we get the same knot. It's the trefoil. How are these related? So one has the one fraction is -3, the other fraction is 3/2. How are these related? They are related by this modular arithmetic relation, 2 equals -1 modulo 3. So 2, the denominator, we notice that they both have the same numerator, 3 and 3, both fractions, and denominators are related by this, they are equal modulo the numerators. So that's one. That's one instance where two rational tangles, different rational tangles, can give rise to the same rational knot. Another obvious instance is when we take palindromic rational tangles. These are rational tangles with palindromic fractions. So one is 2, 3, 4. The other is, we start from here untwisting, so it is 4, 3, 2. So we notice that one fraction is 30/13. The other fraction is 30/7. Again, we notice the same numerator. The denominators now are related through this modular numerical arithmetic relation. 7 times 13 equals to 1 modulo the numerator. And so these two characteristic examples, we'll see that these are all that come in the classification theorem, which is very powerful. So this was done by Schubert, 1956. Schubert used the classification of length spaces for proving this theorem. So the theorem says that two rational knots are isotopic if and only if the fractions to which they are related, P over Q and P prime over Q prime, have the following, satisfy the following relations. The two numerators are equal, and the denominators are either equal modulo P, or their product is 1 modulo P. Okay, we'll see how now this theorem will come later, very soon now in some applications to biology. Just to add here that the first 26 knots, with the exception of 2, are rational. So really it is one of the easiest families to start creating, for creating knots. And we move to now an application to DNA recombination from this theory. So we recall that DNA consists in two right-handed polynucleotide helices that twist around the same axis, the backbone, so as to form a double helix. And each helix has sugar and phosphate salt molecules, and every sugar molecule is connected to one of 4 bases: adenine, thymine, guanine, and cytosine. Now, the geometric structure of DNA is that the bases are placed in the interior of the double helix in planes parallel among themselves and in the interior of the double helix here. Then they are bonded in pairs, the bases, like adenine always is paired with thymine and guanine with cytosine, like making like a zip. It takes about 10 to 10.5 base pairs for a full turn of the double helix. Okay, and as scientists like to say, the DNA molecule in the cell nucleus is like 20-kilometer fishing rope in a basketball. So you can imagine the huge complexity that such a molecule has in the nucleus. The basic functions of DNA is the packing and supercoiling, which in fact protects its structure, transcription, replication, and recombination. And we add here that we also encounter in nature circular DNA, where helices of linear DNA may close with phosphodiester bonds. So this could occur, let's say, in some situations, in some species. Now, circularization can trap knots which can be revealed through gel electrophoresis. And this starts becoming a big problem for the DNA function. Now, here we show the topological model of DNA, as it is just a band with the two borders connected through the bonds, which are the pairs of bases connected. And here we see something. First of all, if we take a linear DNA and we in the relaxed state and we close it, we obtain this B. Then, if we unwound one full turn, we get state C, but this gives some torsion in the backbone. In order to relax again, from the stress, it folds into a supercoil. And this is exactly the ingredients of what we call the equation of life for DNA, which is that the linking number of the border components of the helices, which is a topological invariant, which is a knot invariant, equals the twist, which is the total twist of the backbone, which is a geometric invariant, plus Reith, which is also a geometric invariant, and Reith is the amount of coiling of a closed simple curve in 3 space. So this equation was due to Kalougareanu, 1961. And now let's see, to our concern here, a closed DNA molecule may form locally non-trivial knots. So the problem is, and here we see indeed that a closed DNA molecule that was found by Cosarelli and Spengler in an experiment in 1985. So we have knotted DNA, and the problem is that when this cell has to replicate, the two knots, the knotted DNA has to split in 2 copies. So there must be, and there is an unknotting mechanism by enzymes that locally simplify the DNA molecule. These are the topoisomerases, TOP1 and TOPO2, where the TOPO1 makes a crossing change in the DNA molecule, and the TOPO1 relaxes the torsional stress. Okay, so how do we detect knotted DNA? With electrophoresis in agarose gel. And scientists noticed, people noticed that the ones with a smaller number of crossings, the easier ones, come to the top, and the more complicated ones stay further down to the bottom. So that's how they are distinguished. And now we see, let's talk about DNA recombination. So we have a substrate, which is here a supercoiled double helix. Something happens in some recombination experiment, and we see the products that could be a supercoiling DNA, could be a knotted DNA, could be linked. So what is the mechanism behind this? That's the question now. Here we see, indeed, not a DNA in such recombination experiments. And the answer is given by Ernst and Sumner, at least the first answer, who formulated the Tangle model for solving such equations as follows. First, they showed that all unknowns, so we have here, you see, a substrate S, we have a tangle. According to our operation, what we defined as operations, we can see it as an addition, that we add these two tangles, and here is the result. Again, here it is a substrate. It adds to some other two tangles, the recombinant, which we don't know, this is the unknown. They add, and we get a numerator closure, and we see this product, not. Okay, so Ernst and Sumner showed first that all unknowns in such tangle equations, numerator of substrate plus recombinant equals a product not, are rational tangles. So that was the first observation. Then we observed that numerators of sums of rational tangles are rational knots, and these are fully classified. Then we must find solutions to the given tangle equations. So from which possible fractions, that means rational tangles, arise these specific rational knots that we observe, and from which possible combinations of sums. So that was the model of Ernst and Sumner's oversimplified in description. And they also showed that after the third repetition, they could predict all next resulting knots. So here is what the succession of these experiments, okay, the first experiment that Ernst and Sumner solved. Here is an example of given a rational, the numerator of an original rational tangle, to find all possible cuts that we can cut in 2 points and give rise to rational tangles. So this is a full, let's say, exhibition of the theorem of Schubert. These are all possible places, and all these, if we take the corresponding fractions, they will be related by the modular arithmetic equivalence described by Schubert theorem. So now I make a small interlude, because we will change subject, go to another application in life sciences. But before that, let me say that since we make a small digression from all this mathematics, knots and bonds have been used from early years for medical purposes. Here we see a bond, a knotted bond made by Heracles, who was a chiropractor in the 1st century AD. Also, let me point out to you that there is a whole theory about knots that are made in the surgeries by surgeons. So they have even, these are the arthroscopic knots, and they even have, I think, a medical magazine called Knots, and it treats all these properties of such stitches and knotted stitches that can be used for various operations. So as I said, we move to a different now story, and we look at knots and graphs. So an abstract graph, G, consists in a set of edges, E, and a set of vertices, V, which are connected, and abstractly we don't care how they are connected. All we want to know is that which vertices are connected among themselves with edges. Now, knots are intrinsically related to graphs. So this is a handwritten note by Lou Kaufman from his book Notes in Physics. Here we see knot diagrams that give rise to planar graphs, which are like dual objects in the diagrammatic setting. And here is the full analogy of the isotopy moves, the Reidemeister moves, how they are translated in terms of graphs. But here we care more about spatial graphs, that means graphs embedded in 3 space. So what the definition we gave before and what is mostly known is the abstract definition of graphs. Here we care about how they sit, the graph, how it sits in 3 space. One of the early results is by Conway and Gordon, who proved that a full graph of 6 vertices, K6, has always, no matter what embedding, has always two linked triangles, two linked closed components. And that the full graph of 7 vertices has always one non-trivial knot sitting inside. So embedded graphs are also considered in 3 space up to isotopy. This is the equivalence relation we care. And they extend classical knot theory. So the study of embedded graphs is an extension of classical knot theory. And in this area also, Lou Kaufman has made very fundamental contributions. And I also note here other people have worked in the theory of embedded graphs, like Kaufman with Vogel, Zezé, and so on. And all this, we mentioned all this in order to talk about molecular graphs. So a molecular graph is the representation of a molecule by a simple graph, so that the vertices represent atoms and edges represent chemical bonds. Okay, and here we are very interested in chirality or handedness. An embedded graph, so the chiral, let's say the mirror image, if we see a graph through a mirror, we obtain the mirror image of the original graph. So an embedded graph is topologically achiral. That means it cannot distinguish between its mirror image if it is indeed isotopic to its mirror image. A molecule is chemically achiral if it is, if the molecular graph is achiral, and moreover, we can compose in the lab its mirror image. Note that all planar graphs are chemically achiral. And now, a special case of isomers, which come next, is enantiomers, which is a pair of mirror image molecules that are chiral. That means that one is distinguished from the other. Okay? Why we care so much about chiral? Because these are the easiest, if we want to construct in the lab, these are the easiest to start with for constructing something new. And here there is a note about thalidomide, which is a chiral medicine composed by both enantiomers of the molecule, which in the 60s, one acted as doctors expected, but the other caused problems to the embryo in pregnant women. So indeed, the chiral molecules could have quite different physical properties and functions. So, chemists, as I said, or scientists are interested in constructing in the lab new molecules or new materials whose structure is related to somehow to the original molecule, but not so far. Let's say they want to capture some features and maybe improve or create some new ones. These are called isomers, and we have 3 types of isomers. The structural type, which is the same molecular type but different molecular graphs. Geometric, which is the same abstract graph, but as rigid objects, they cannot superimpose. And the topological isomers, which have the same abstract graph, but as embedded graphs cannot be isotoped. So, to make it a bit shorter, if we know that the knot is chiral, then this implies chemical chirality and geometric chirality. So it might be worth constructing it in the lab. Okay, for example, here we have the figure 8 knot. The Jones polynomial is very good for detecting chirality And we have here the figure 8 knot that we see that it is achiral. So it hardly makes sense to construct something in the lab with a figure 8 knot. Whilst the trefoil is chiral, and indeed the molecular trefoil is also chemically chiral. And as a more general powerful technique, again due to Kaufman, we construct for embedded graphs a set of nodes by unplugging the vertices, and the result is that if this set of resulting nodes contains a chiral element, then the original graph is chiral. So this is extremely powerful. Now I want to go a bit faster. This is another example applying this result, this technique. But I want to go a bit faster. We have for rational nodes, if we want to construct a rational knot in the lab, we know that it is chiral, so we should avoid constructing, if and only if the continued fraction is palindrome, it's fully palindrome. So that's a very nice and perhaps useful result too. And here is about graphs, molecular graphs that are modeled topologically by Möbius ladders with bonds, two bonds. With two bonds, they are always achiral. With three bonds or more bonds, and Simon proved that with three or more bonds, a Möbius ladder molecule is always chiral. And okay, so now we want to move on to the third application about proteins. So a protein is a large, complex, open-ended molecule which is essential for life and is made up of amino acids linked together by peptide bonds. So a protein has a unique three-dimensional structure that determines its function. And this structure is determined by the sequence of amino acids and how they fold due to the presence of the bonds. So I will make it a bit faster. Scientists model proteins by, so this is the secondary structure, let's say, band and curve simulation. And at the bottom, we see the protein 3-KZN, which has open ends, which in the more simplified model to the right, they are supported by two parallel lines. In some proteins, there are some knotted structures that are observed, and to only about 1% of known proteins, we observe knotting, but these knotted proteins provide important information about protein folding and stability. But not only that, it's not only about the discussion here and the application, it's not just about this 1% of proteins, it's about the full 100% that we will talk about. So traditional knot theory, in order to study proteins and classify for the protein database, traditional knot theory requires closed loops. So with proteins, people connected their ends artificially, for example, via a direct segment connection, and then they determine the knot type of the resulting closed loop. And this characterizes the protein. But this approach is very sensitive of how this closure is performed. Then we have now the theory of notoids, which you see that it starts resembling a bit proteins, or that it is rather, it has to. So the theory of notoids developed by Turaev in 2011, we heard it for the first time. It is a diagrammatic theory of open-ended curves immersed in some surface, the sphere or the plane, with the two endpoints trapped in the regions. They cannot go beyond the region, otherwise trivializes. Notoids are related to knots by connecting the ends, of course, over or under, and you see now how sensitive this connection is, what we said before. Because here, if we make an under closure connection to the notoid, we see we get a trefoil knot. To the other, with an over-connection, we get a trivial knot. So, Turaev showed that the theory of notoids in the sphere extends classical knot theory, yet another extension. Kaufman with Neslihan Gugumcu, they made this amazing lifting of notoids in 3 space, which immediately now alludes to modeling proteins. So, the first work for using notoids to model proteins and study proteins goes by Guntaroulis, Dorieben, and Stasiak. And they obtained as good results as the end-to-end closure using virtual crossings, which is another big theory due to Lou Kaufman. So here we see, if we use for the protein 3-KZN the uniform closure, we obtain this set of knots, a very small set of knots related to this protein. This is the knot atlas related to the protein. According to the different projections we may have on the sphere, we have the protein enclosed in a sphere. And we project it on different planes, say 1 million different planes on the sphere. Then we check what, and then we also close the protein. Either we close by connecting to points in the sphere, okay, and then we examine the knot types that we obtain. So using this uniform closure, we see that we obtain only 4 different true knot types, apart from the trivial, with the uniform closure. Then if we project the protein on like million planes on the sphere and take the notoids that we see, if we use spherical notoid theory, we see all this set. So the protein is characterized by all this set of knots that are formed by this protein. And you see this blue is the dominant knot, which is the trefoil in this case. If we use planar notoids, we get even more information for a protein. Okay, thank you. So, and we see here a much richer set of knots related to the same protein if we use the theory of planar notoids. So anyhow, so all these have been extremely useful for the protein database. A leading figure of which, one of the leading figures is Joanna Sulkowska. And then we went on for the 99% of the remaining proteins which do not exhibit knotting. We went on and we introduced the theory of bonded notoids. So where the protein has bonds, we model it by notoids which also have bonds. These are arcs, simple arcs embedded in the complement of our link, so that their boundaries intersect the link transversally in distinct points. So these orange arcs simulate the chemical bonds in the protein. Using this now, we get a much richer results, because here, for example, you see we have this type of bonds, sequential, nested, pseudo-knot-like bonds, which, if we forget the bonds, we just have simple arcs, nothing. So we cannot distinguish anything here, just unknotted, nothing. It's like the 99% that we were talking about. So it was really the bonds that made the difference here for distinguishing these different sides of the protein or the proteins. So here then one could use another technique that we also learned from Lou Kaufman, which is the tangle insertion, where at every bonding site we insert a tangle. We replace the bond by a tangle. And then this, you see, they look much more complicated objects of knot theory. And then, of course, we apply to them known invariants, and then we tell them apart. So this is also a very powerful technique, and also with recently with Yannis Diamandis, who is one of the organizers of the meeting here with Sonia Mahmoudi, And with Lou Kaufman, we also define the bonded closure, because there are some studies where open ends in molecules close by chemical bonds. So this is also perhaps something interesting to have. Then, okay, so I'm coming to an end. So I'm saying that all this, what we said, DNA, proteins are polymers, okay? But the polymers have much more, much more into it than, so I will go fast with these slides, because it is just to give you an idea of how much also the study of polymers is related to life sciences, of course, as most of you know. And therefore, studying of polymer melts is also something that knot theory can lend methods and techniques. So a polymer melt is like what they call sometimes like a spaghetti, a cube full of spaghetti. It can be modeled by a basic cube undergoing 3 periodic boundary conditions. Otherwise, the complexity is huge. The pioneers in the topological analysis of linear polymers, linear means with open-ended chains, are Djoumanekas and Theodoru from my university, chemical engineers. And there we have Eleni Panagiotou, who has worked a lot. She defined the periodic linking number for 2 and 3 periodic boundary conditions for open-ended chains, which was quite a hard problem, and many more very important recent results. And here in the audience, of course, we have the organizer, the main organizer, who is Sonia Mahmoudi, and she is, in a different context, she is another expert in 2 periodic boundary conditions and weavings, as we will learn more next week. And I close with this nice picture of back in 2011, in May, in Switzerland, the Quantum Topology Conference, we heard Turaev announcing his theory of notoids, and we see here Yannis Diamantis, Von Jones, this famous mathematician. Here's Lou Kaufman, the other famous mathematician, myself and Eleni Panagiotou, and along with many other people, all this except Jones have been involved and have made very important contributions in the theory of notoids and the study of polymers. So, in conclusion, knotted and entangled mathematical objects are used for modeling entangled structures in life sciences, and modern techniques of knot theory inform on their function and physical properties. On the other hand, physical entanglements in life sciences inspire and provide a frame for developing new topological theories and not theoretical techniques for measuring their complexity. So, and as you may think that I finished, no, I show you here that knots are not just mathematical objects, they are also practical, they are artistic and symbolic, they are ornamental, they are decorative, they have appealed to great geniuses like Leonardo da Vinci and Albrecht Dürer, geniuses like Escher, the Möbius trefoil here. They have inspired colleagues like Slavik Jablan, who made these amazing pictures, or they are even intriguing structures, always an endless source of inspiration throughout history, from Celtic knots and going backwards from Celtic art to Chinese knots, really beautiful, mostly alternating, Japanese knots, beautiful for packing, ceremonies, and so on. I go this very quickly. I just wanted to relax you from all this mathematics. And yes, and I will close. This is really the last one. My favorite logo using the Borromean rings, where we connect the spirit, the soul, and the body in the 3 rings. That was the logo that we used in the conference Knots in Hellas in 1998 in Greece. And I thank you. Thank you for all this.